So now we've gone through the types of classes. We can now start talking about unsupervised classification. So unsupervised classification is just identifying sort of natural groups of spectrally similar pixels, or we sometimes think of this as structures in multispectral data. So for instance, if you were looking at the distribution of points or pixels within a graph, again, band 3 versus band 4, you might see structures, you might see places, and you will see places as we move along with this, where there's a whole bunch of points. So that's how we think about it, as sort of a little structure within the data set. And in general, it can be demonstrated that remotely sensed images are composed of spectral classes that internally are relatively uniform with respect to brightness in several spectral classes. I mean, you generally don't have, for instance, you have fields of corn, fields of wheat, fields of soybeans. You hardly ever see a field that has a mix of all three species, right? So just because the world is organized that way, images are organized the same way. They generally tend to have different spectral classes that are uniform with respect to each one of them and then distinct from other spectral classes. And unsupervised classification is just the process of identifying, labeling, and then mapping those classes. So unsupervised classifications are going to be more or less simple algorithms that don't require a lot of input information or a lot of tweaking as they run, okay? And they're just going to go pixel by pixel and identify clusters or groupings of data within what we'll refer to as feature space. So assuming there are clusters apparent in the image data, this is done by calculating the distances between specific pixels within this feature space and assigning them to cluster centers. The technique that I prefer is ISO-data, the iterative self-organizing data analysis technique. It only requires a few parameters. For instance, in the program ERDOS, it only requires that you tell it how many classes you want, and a rule about how many pixels must remain unchanged between iterations. So this is, as it says, an iterative technique. It's going to look at the data multiple times. And when each subsequent look is going to change the assignment of pixels to clusters or classes. When the amount of change falls below a given threshold, and the default is 95%. If 95% of the pixels don't change class, then that's the point at which the clustering process will stop. Or if the number of iterations, the number of looks at the data exceeds a given number that you give it, then it will also stop. So you have to tell it how many classes you want. You have to tell it what percentage of pixels can remain constant to force the iterations to stop. And then you need an alternate criteria for that stopping, the number of iterations. So now we'll talk about feature spaces. The way we've talked about spectral qualities so far has largely been using the idea of a spectral signature. That is, here we have three different surface types: soils, vegetation, and water. And we have the sort of continuous spectral signature, what the reflectance is as a function of wavelength. And then we have two bands there, band 1 and band 2. And we're going to figure out how bright the reflectance is in each of those bands. And that's what the sensor is going to do, right? It's going to come up with a number that tells us how bright or how reflective a particular pixel is for a given wavelength, wavelengths 1 and 2. So that's the sort of spectral space. On the right is the feature space. And in the feature space, we're once again plotting one band against the other. So wavelength 1 band and wavelength 2 band. And again, this is essentially you're looking at bands 3 and 4 from Landsat, red and near infrared. And so whereas water has low values for both wavelength 1 and wavelength 2, we can see that in the spectral space, but then in feature space, that just means that that water pixel is going to be near the origin. Going back to the spectral space, we have sort of a higher value for soil in band 1 and a moderate value for band 2. So what we're going to find is, soil is going to have a high brightness along the band 1 axis and a moderate value along band 2 axis, and supporting the idea that this is a red near infrared space. Vegetation has low values or a low value for wavelength 1 and a very high value for wavelength 2. And so it's plotted, sort of a little darker, it's shown, than soil in the feature space, but much higher in terms of wavelength 2. So this is the two complementary ways of looking at the spectral qualities of particular pixels, or these could be averages for a given class. They can represent different things. In this case, we're going to talk about them or think about them as individual pixels. The way we use this feature space is we're going to say points that are closer in feature space are more similar. That makes sense, right? I mean, it makes sense in either space. In the spectral space, if you had two lines that, almost overlapped, then you would say, oh, those two things are similar. Well, in the feature space, that's all translated to where you are, what your position is. And then if we have a unknown pixel, right? So here we have this peach colored pixel. We don't know what it is. We can look at the distance between that pixel and known pixels, right? So that you can say, well, this pixel is closest to vegetation, for instance. I think actually it's pretty much equidistant. And therefore, I'm going to call that pixel vegetation. At the simplest level, this is the role of classification rules, is taking unknown pixels and comparing them to known pixels and assigning them a class. And, we usually look at these things in 2 dimensions, but we can look at them in 3 dimensions as well. So doesn't matter what kind of image it is, band 4, band 5, band 6, and we have 4 classes. Each one is denoted with a letter. It's W, A, O, or M. And you can see that in this case, we're displaying the fact that there's variability. right? Because no two pixels, I mean, some pairs of pixels will be identical, but if you look in a forest, we keep using this phrase like near uniform. You know, not every pixel in a forest is going to have exactly the same spectral quality. It's going to depend on species composition, density, slope, aspect, all the things we've talked about. So there's going to be some variability, and whereas in the last image, we didn't look at that variability, here we're sort of not only looking in 3 dimensions, but also showing you the variability. So now we have the tools in hand to start thinking about how we're going to do an unsupervised classification. And the first step in the ISO data process is we need to come up with a series of guesses about where the original class locations should be put. That is, let's say in this case, we're going to have 5 classes for our unsupervised classification. Because those classes will be defined ultimately by where they're located within feature space, we need to have a preliminary guess at where those classes would be. And the easiest thing to guess is to simply say, well, they're going to be evenly spread within the feature space relative to the mean and standard deviation of each spectral band. So here we're looking at band 3 versus band 4. Again, we'll just assume it's Landsat. And this little hat-like shape, if this reminds you of the tassel cap, this is not a mistake. This is the projection of a tassel cap into band 3 and band 4. Let's say that line, that shaded polygon, that's where 95% of the points are. We're not going to draw the points because that's, it would just make a mess out of it. So that's where the individual pixels are located. 95% of them are within that little hat looking object. Now we're going to add to that a guess about where the clusters actually are within that space. And we're just going to take the mean. You can see on each axis, you've got the normal distribution with a mean and plus or minus 1 standard deviation. So 66% of the data will be included within plus or minus 1 standard deviation. And we're just going to lay out points evenly between -1 and +1 standard deviation from the mean. And we're going to do that for each one of the bands. So you can imagine that you had a table, and in the on the top of the table you'd have bands 1 through whatever n, and on the x-axis you would have, the y-axis, the rows of the table, you would have class 1, class 2, class 3, and you would fill in, for class 1, the band for the value for band 1 for class 1 would be -1 standard deviation below the mean value for band 1, and it would be the same for band 2, 3, 4, 5. They're all going to be at the lowest end of the distribution for each of the bands. And band 2 would be that next one, and it would also have that next higher value for each one of the bands. So in this case, it's half a standard deviation below the mean for bands 1, 2, 3, 4, etc. All the way up to +1 standard deviation. So in the first step, we're going to look at all the pixels that are within that within the image, and we're going to ask the question, which cluster mean position is it closest to? Okay, we're going to assign every pixel that's closest to a particular mean position to the cluster that has that mean position. Okay, so at this point, all we've done is assign those pixels. So the ones all the way out at the tails of the distribution, you know, the sort of the pointy bits at the three edges of the hat, are going to be assigned to whatever pixel whatever cluster they are closest to, even though they're quite far away. Because the rule is every pixel has to be associated with one cluster. We're then going to recalculate the average position of each cluster. And so, in particular, clusters that are near one of those three edges or 3 points are going to be moved toward the extreme portion of that distribution. Because now you have a whole bunch of pixels with very low values for the first cluster or very high values for the last cluster that are going to be taken into account for the average of that particular cluster. And in addition to showing these clusters, we can now talk about these ovals. And those ovals just show the 95% confidence intervals for that mean value, okay? And there's some overlapping, okay? Because it's so highly variable, there are going to be some areas where pixels could just mathematically be assigned to one or the other cluster. And this is why, as we go forward, pixels are going to move back and forth between two clusters. So once we've decided, or once we've calculated new cluster means for each one of the clusters, we're going to do the same process. We're going to look at all the pixels and then say, oh, well, now which cluster does that particular pixel belong to? Because the cluster mean may have moved far away from or further away from a particular pixel. So now another cluster mean might be closer, okay? And so the process begins again of reassigning pixels, recalculating cluster means, and then doing a check to see what percentage of pixels have changed class. And once you get to the point where you've met your criteria for the fraction of pixels that are not changing, or we run out of iterations that we've specified, we're just going to keep doing this, okay? And as you can see, as you get, at least in this sort of imaginary space, this cartoon version of how the algorithm works, you now have classes that are very much associated with the three extremes of the distribution. You know, the one that's got low values for band 3 and band 4, the one that's got high values for band 3 and band 4, and then that circular one up there that has moderate values for band 3 but high values for band 4. And this is an example of what you would get if you started not with 5 classes, but 20 classes. And again, there's the distribution of brightness values. You know, say the 95% of all the pixels fall within that brown or grayish polygon. And here we've set up a series of initial guesses for the position and variability of each of the classes. Then after 20 iterations, this is, at least in the cartoon version, what you get is individual clusters have moved in the direction of such that they are overlapping with most of the places where you have pixels associated with the image conditions, right? So like 20 has moved out to take over that one lobe that was in the data. 18 has moved out. Otherwise, you see they're mostly just clumped in the middle. Now these are 2 standard deviation intervals for those ovals. So there are some places where there just aren't a lot of pixels that don't have a class associated with them. So for instance, that area of gray space between 18 and 20, if you look at all the gray space, that should be about 5% of the data is hanging out in those areas, and they just haven't affected the individual cluster means or cluster standard deviations enough to pull a class over to cover that particular area. Okay, that's the theory, and that's the set of images that are used 99% of the time to show the concept of ISO data. What I did was to look at our usual TM3432C, okay, just take a subset of that, and did successive ISO data runs with greater numbers of iterations, okay? So I started out with, I just ran it once and recorded the positions of the cluster means, and then I did it twice and recorded those positions. And so you can actually see, using this data set, how the cluster means changes as a function of iteration. And so in the next couple of images, I plot a white line to show the trajectory of each of 8 classes that I use for ISO data. And then at the point where they end, I put in a black diamond, so that's where their final position was. And I then also put in an ellipse, which, depending on which one you're looking at, is either 1 or 2 standard deviations to show you the variability of the final class. So here we have near infrared and red, so bands 4 and 3. We have the white line, so if you look at, say, class 8 in the upper right, you can see where class 8 was originally located based on just the guess of the computer, and where it moved over the course of the iterations that it went through until it finally winds up at that black diamond. And then the circle shows you 2 standard deviations. I'm sorry, 1 standard deviation for the pixels associated with that particular cluster. And so you can imagine, even though you don't have the larger number of standard deviations, that cluster includes all the areas to the right and up from there, all those, relatively infrequent points. In case you don't remember, areas in this image where you have red means there are a lot of points in the images. Areas where you have green or cyan or blue or purple, those are areas where there are not a lot of pixels. So cluster 8 the mean is not very far out toward that northeast. You can think of it as northeast, or you can think of it as upper right, because there just aren't a lot of pixels there. The average position is still within that area where that's yellow. So you can see 8 moves quite a bit, and you can see 5 moves quite a bit, and you can't see the label, but 1 moves quite a bit, the one down near the lower left hand corner. But not a whole heck of a lot happens with the intermediate numbered clusters. So this is 2, 3, 4. They move, but in fact, in some cases, they move one way and then they move another way, and don't necessarily wind up, class 2 essentially doesn't move at all. You can't see a white line there. It's all covered by the black diamond. But there's some interesting things that go on with clusters 4, 6, and 7. And they do move to fill in an area. For instance, cluster 6. I hope you can see that right there. It's the one that's well, in the lower right-hand corner, you can see the last little bit there of cluster 5, and then right above that is where cluster 6 is. And you can see as cluster 5 gets moved out to take the position of high near infrared, low red, cluster 6 kind of gets dragged along with it in order to as points closer to the center point of cluster 6 become further and further away from the center point of cluster 5. Then this is band 4 versus 3 thematic. So this shows you which class winds up in which or which cluster each pixel is associated with. In particular, what's interesting is if you look at that first cluster down there at the lower left, you have the mean position of the that cluster has very little to do with, and if you go back one slide, if you can do that, you can see that down right near the origin, there's a whole bunch of points that are water points. And those are classified as class 1, but in fact, the mean class 1 position has nothing to do with water itself. So in this case, your thought as a remote sensing scientist would be, well, I just didn't put in enough clusters. Now, you can see that we have mixes. It's not a clean, there's no clean boundaries between each one of the color-coded classes. And that's just because we're only looking at it in 2 dimensions. Some pixels in some of these subsetted areas where there are mixed pixels would be closer to one or the other class in some other band or set of bands. So there's no clean boundaries. If we had just used band 4 and band 3 as the class for this classification, there would be clear boundaries. But that would have been not making good use of our data. And so this is what the classification winds up looking like. Band 1 purple, that's mostly water. It is also, though, dark forest. And you will find that this is a problem in any place where you've got the combination of well-developed forests and rugged topography, that your north-facing forests, so forests on north-facing slopes, will be very dark. Not as dark as water, but fundamentally, as you've been able to see with the unsupervised classification, the forest is quite similar looking to water in the overall context of looking at all the pixels, okay? Which is what the unsupervised classification is doing. It's saying, well, we've got a whole bunch of pixels. All of them need to be represented to some extent. And within that context, these 2 land cover types are essentially identical as far as the algorithm is concerned. So we already talked about this, how many classes are enough? Clearly, the number of classes I used for this little example weren't enough because the water did not come up as a distinct class. It's actually in these kinds of cases, very difficult to get water to come up as a distinct class. But, you know, if you have too few, and we probably have too few here, you're going to have numerous cover types, real cover types in the real world that are going to share a particular spectral class. I should say that very often when you do get this mix between water and shaded forest, heavy shaded forest, the thing to do is to take all the pixels that belong to those two classes and do an unsupervised classification just on those two classes. So mask everything else out. Because if you do that, in that context, the distinction between the two classes becomes quite obvious mathematically. So we've seen the case where there are too few. If you have too many, you're going to wind up with redundant classes. So you might wind up with 4 kinds of water, which is okay sort of in theory. In practice, you know, if you wind up with creating 70 classes and you wind up wanting to recode them to say 12 classes, it's just a lot of manual labor that you have to do to, you know, convince ArcGIS that it wants to do recoding with that many classes. So either way, you're probably going to need to break up some classes or combine classes before you have a final product that you're comfortable with. The way that identifying each class, what that workflow looks like, you know, you start with, in the upper left-hand corner, your original image. You set up your unsupervised classification and tell it the number of classes you want and what the stopping rules should be. And then you get basically just a black and white image in general, where each level of gray is just the average brightness of a particular class, but the data in the image itself is class data, which if you do what's referred to as a color slice, you do this in ArcGIS, right, in the symbology plane, and you assign a different color to each one of the values associated with the unsupervised classification. You see now you can see all the different classes. Again, that's not spectral information. Those are just colors that have been assigned to thematic classes. The next step, you'd make everything a neutral color, white or gray, and change each one of the classes in turn. So in this case, I've made all the colors white, and then I went back and made class 8 green. And just looking at the original image, using that informal knowledge that I have about the scene, I can tell, oh, well, those are green agricultural fields. And so for some purposes, that may be enough. You know, particularly if, for instance, if all you need to know is, you know, a rough estimate of how much agriculture there is in this small image subset, you might be able to go in and say, okay, well, I've looked at all these classes, 1 or 2 of them are clearly agricultural, and now I'm just going to sum up those values. To have a better notion of what your accuracy is for more detailed purposes, you're going to have to do an accuracy assessment, and we'll talk about that in the next lecture. And this is your final product. You basically just go in and assign class names. You can see that on the right-hand side of that table, and you assign meaningful colors, and that gives you your unsupervised classification. Now, the unsupervised classification, even though it's giving us the image in one, one step. Fundamentally, what it's done is assigned average and standard deviation or variability of the reflectance or digital numbers for each one of those classes that we've now identified using the identification procedures. Okay, so that gets us back to the spectral signature for each one of those classes. Advantages of unsupervised classification: there's no extensive prior knowledge of the region that's required. Knowing as much as you know about Fort Collins and the area around it now, you ought to be able to look at an unsupervised classification and assign labels to each one of the classes. Oh, well, that's Horsetooth, and it's class 7, so class 7 must be water. And then, you do a little due diligence to make sure everything that you've called class 7 is actually water. Then you can move on to your next one. Sometimes it's going to be more confusing like that, particularly when you have questions like pasture or rangeland. In general, you probably have a pretty good sense for what the majority of the classes are and where they are in this area. And if not, get out, travel around a little bit. Or, that's a joke, you could use aerial photography. For instance, you could use NAPP or NAIP data and figure out what you're actually looking at and say, oh, well, look, I see, there are cows being grazed land there, so that's a pasture area. So you don't need a lot of prior knowledge of the region. The opportunity for human error is minimized. What we're going to see with supervised classification is that the biggest source of error you're going to have is just your ability to identify good training samples for the supervised classification. And in general, if you have something unique that you might not have considered, like, for instance, what's a good one? Particular roof types, for instance. If you had like a lot of red clay Spanish tile roofs and you didn't necessarily think about that before you started the classification, unsupervised classification is going to pick up that unique spectral condition and assign it a class. The disadvantages are, unsupervised classification are rely on natural groupings or clusters, and matching them with what's actually going on in the real world is not necessarily the easiest thing to do. So spectral classes are not necessarily information classes, okay? You have very little control over the image classes, okay? So for instance, again, let's see. I'll do, if we're doing mixed forest, conifer forest, and broadleaf forest, the unsupervised classification may always determine those as a single class, or it might just split it into two classes. And basically the only way you can get finer control over that is by increasing the number of classes that you're using. And so that makes it very difficult to come up with classes that you can rely on the definition. There's always a certain fuzziness about it. And once you have an unsupervised classification, it's only applicable to the data you've used it from, okay? Spectral properties are going to change over time. You're not going to be able to take the information from an unsupervised classification and apply it to another scene necessarily.